You know, we all learn in school that gravity is what keeps our feet planted firmly on the ground. It feels, well, constant, right? Unchanging, dependable. But what if I told you that's not really the whole story? What if there are places on our planet where gravity's pull is just a little bit weaker? A tiny discrepancy that actually hints at a massive connection between the planet's molten guts and the ice at its poles.
So let me just ask you straight up. Is Earth's gravity the same force everywhere you go? Well, the answer, maybe surprisingly, is a big nope. Not even close. In fact, our planet's gravitational field is full of these invisible peaks and valleys, a whole complex landscape that scientists have been mapping for decades. And it turns out the deepest valley of them all is hiding right under the ice of Antarctica.
Now, you might be thinking this difference is, huge. But for a person, it's tiny. If you weigh about 198 pounds, you'd weigh about 5 or 6 grams less in this spot. You would literally never feel it. But that super tiny, imperceptible change, it's actually a massive clue pointing to a colossal process churning deep, deep inside our planet.
To really get this, we need to talk about something called the geoid. So first, you gotta throw out that image of Earth as a perfect shiny blue marble. A much better way to think about it is like a slightly lumpy potato. The geoid is basically a model of what the ocean would look like if there were no tides or currents. It's shaped only by gravity. The high spots are where gravity is stronger, and the low spots, well, that's where it's weaker.
And this brings us right to the heart of our mystery. The biggest, most dramatic dip on that entire gravitational map is what scientists call the Antarctic geoid low. For years, they've been scratching their heads, wondering what on Earth could cause such a massive anomaly, this so-called gravity hole, right underneath the South Pole.
Okay, so to crack this case, we're basically going to become scientific detectives. We'll start by seeing how we can weigh the Earth from space. Then we'll dive deep into the mantle's super slow dance to figure out what's causing all this. After that, we'll explore the surprising ripple effects and finally connect our planet's climate to its fiery core.
Our investigation starts way, way up, in space. To solve a mystery that's happening thousands of miles beneath our feet, you're going to need some seriously high-tech gear. So, how in the world do scientists actually weigh parts of the planet from orbit?
The way they do this is just brilliant. Missions like GRACE use a pair of twin satellites that are basically playing follow the leader in orbit. Now, when that first satellite flies over an area with a bit more mass, a gravitational lump, it gets pulled forward and speeds up just a tiny bit. This makes the distance between the two satellites grow by a microscopic amount. And by measuring that distance with insane precision, scientists can build an incredibly detailed map of Earth's entire gravity field.
But here's the thing. Those satellites can only map the effect of gravity from the outside. To understand the cause, what's actually happening down in the mantle, we need a way to see inside the planet. And to do that, scientists turn to one of the most powerful forces there is, earthquakes.
One of the study's authors, Dr. Alessandro Forte, put it perfectly. He said to imagine doing a CT scan of the whole planet. But instead of X-rays, you use earthquakes. The seismic waves from these quakes are like the light that shines through the Earth's interior. By tracking how those waves travel, how they speed up, slow down, or bend, scientists can build a 3D model of the mantle, just like a doctor's CT scan.
So now we have our tools, right? We've got satellites to map gravity's effects and earthquakes to peer inside the Earth. And with these, researchers could finally get to the good part. They use these seismic CT scans to build these super powerful computer models and essentially rewind the clock, watching the slow, churning dance of the mantle backward for 70 million years.
And here is what they found. That gravity hole under Antarctica, it's not a literal hole. It's a mass deficit. It means there is simply less stuff, less mass, in that region of the mantle than there should be. And this deficit is the result of this epic, slow-motion battle between rising hot rock and sinking cold rock.
The computer model showed this whole thing didn't just happen overnight. About 65 million years ago, right around when the dinosaurs checked out, the gravity anomaly was there, but it was pretty weak. Then, around 40 million years ago, something kicked into high gear. It started getting way, way stronger, eventually becoming the massive feature we see today. So what was happening deep underground?
Well, the answer comes down to two opposing forces. On one side, you've got these huge plumes of hot, less dense rock bubbling up from the deep mantle. Less density means less mass, which means weaker gravity. But at the same time, you have these ghosts of ancient oceans.
Cold, dense slabs of old tectonic plates from the long-lost Tethys Ocean are sinking down into the mantle like these giant, cold anchors. It's this combination, the rising hot stuff and the sinking cold stuff, that creates the planet's biggest mass deficit.
So, okay, there's a slow-motion battle of rock happening thousands of miles under the ice. Cool. But why should we, up here on the surface, actually care? Well, it turns out this deep Earth drama has created a planet-wide ripple effect with some very real and pretty surprising consequences for the world we actually live in.
For one, this deep Earth battle literally shapes the surface of our oceans. You'd think sea level would just be level, right? But it's not. In a region with weaker gravity like this one, there's less of a pull on the water, so the ocean actually sloshes away towards areas of stronger gravity, causing the sea surface around Antarctica to be measurably lower. That deep mass deficit is literally depressing the ocean itself.
And this brings us to a really fascinating geological coincidence. Remember when that gravity low started getting stronger? Between about 50 and 30 million years ago? Well, get this. Geologists know that is the exact same time period that Antarctica began its massive transformation from a pretty temperate continent into the frozen ice world we know today. Could the churning of the deep mantle have actually helped kickstart the birth of the Antarctic ice sheets? That is the next huge question this research opens up.
So, you see, this whole discovery isn't just about solving some old geological mystery. It's about connecting our climate to the planet's core and building a much more complete picture of Earth as one big dynamic machine.
What this really hammers home is that we can't think of our planet in separate, isolated pieces anymore. The geology happening way down in the mantle isn't disconnected from the climate up here on the surface. They are deeply, deeply intertwined. And to really understand one, you have to understand the other.
And that leads us to the ultimate question that Dr. Forte and other scientists are now chasing. How does our climate, the very system we live in and rely on every single day, connect to that slow, powerful engine churning deep inside our planet? Figuring that out is going to be key to understanding Earth's future.
In the end, the Antarctic gravity hole isn't just a weird quirk. It's a profound reminder. It shows us that our planet is one single, dynamic, interconnected system, where events that play out over millions of years, thousands of miles beneath our feet, can end up shaping the ice, the oceans, and the climate of the world we call home.